Hey guys, welcome back to another stream. Actually didn't end up going to the mall, just decided to stay in and continue streaming. So right now what I want to do is I finished Chris Miller's book on chip war. I didn't take super detailed notes like I wanted to. I just kind of skimmed through the entire book, and maybe I'll go back a little bit deeper and think about some of the really high level concepts and important concepts to understand. But I do think that there's some interesting things here. So there's types of chips. So he ends up breaking it down into three different things. So the first type of chip that exists really is memory. So this is DRAM, so dynamic random access memory, and then I don't know what NAND is, but I think it's flash memory. So NAND/flash. Then we have logic chips. So these are CPUs, I think GPUs, and then these are third type are specialized chips. Sensors, military. I think these are kind of the three different categories of chips that you can really think about here. So when we think about this at a high level, tailwinds, semiconductor tailwinds. So I think that AI training AI model training and inference. That's going to be a big one, especially with GPUs. A lot of people being companies are training these massive large language models and also specialized machine learning models that really can be trained in parallel. So that's something that GPUs are optimized for. You can do sequential matrix multiplications as many times as you can, depending on how quickly you can scale the amount of GPUs that you're using. So AI model training and inference. We also have 5G network adoption. Internet of Things. So, these might sound like buzzwords, but I think can provide a lot of real value in the future. So the 5G network adoption, I think this is something that was mentioned in the book. There's going to be more data that can be transferred on. So more data can be transferred on existing spectrum. Need to figure out what this means, but I don't know the exact scientific details behind it. But at a high level, it seems like the way that information today is transferred. So let's say you're sending a text message between two different phones. I think there's a specific frequency on the spectrum, which I guess is all of the available frequencies that exist in Earth, and you're sending maybe data through a specific frequency on that spectrum. That data is usually in the form of a wave, so that's where the wavelengths come in. So I think another way of calling this is a signal. Now, I think 5G, it's a way of being able to incorporate more information onto these waves. I don't know exactly how the technology works, but there's also some standardized protocols among different communication devices. Let's see. So it's the full range of all frequencies of electromagnetic radiation. So field is a type of field that combines the effects of an electric field and magnetic field. So fields are an essential concept to physics and mathematics. At a high level, a field is a function that returns a value from a point in space. Okay. Alright, so this is the basic transistor shape. Now, new semiconductors will need to be made in order to adopt this technology. So 5G infrastructure will need to be built out, meaning upgrading existing cell towers. Okay, so let's see, 5G infrastructure. So 5G cell tower maps. So I'm in this area. What do the X's mean? Okay, I guess those are just locations. What's this? .5G ultra wideband capable city. Okay, so I guess the darker red probably means that you don't have access to 5G. So, sorry, darker red means you do have access, while lighter red probably means you don't have access. Okay, and so Verizon only has coverage in the US too, so it's not global. Okay, this could be an interesting thing too. Okay. Internet of Things. My definition of the Internet of Things are electronic devices that are all connected to each other via some type of electronic communication. The signals alerts. So everything today is being digitized, and the semiconductors are the driving force behind them. Okay, so Internet of Things. We also have robots, and I want to say space. I feel like those are some interesting things. Maybe possibly quantum as well, but that might be a little far-fetched. Robots. How many semiconductors are in a robot? Yeah, Bluetooth and Wi-Fi. I have no idea how these work. Processing power, that's fair. How many chips are used in a rocket? Space rocket.
when you cook.
I'm extremely excited about space and space exploration. I mean, there is nothing more exciting than just going out there and being among the stars. As you might have guessed, this video is gonna be a little bit of rocket science. I'm going to discuss the main challenges of chips in space. So, what are the radiation-hardened chips? Which chips are used in rockets like SpaceX Falcon and Dragon, and also which chips are used by NASA? I have to warn you, it's gonna be a little bit long, but very fun video. Traditionally, chips which are used in spacecrafts are far away from the current state of the art. They're lagging by several generations compared to modern commercial CPUs and memory. For instance, the International Space Station, which was launched in 1998, still runs on old 20 MHz Intel microprocessor from 1988. Can you imagine? So, why building chips for space is a rocket science? In space, where the temperature can approach over 2000 degrees Celsius, the radiation is deadly, and you will be traveling at speeds up to 30,000 kilometers per hour. We don't want a microcontroller to shut down once all of a sudden. Traditionally, the chips which go to space must be radiation hardened. Otherwise, they may fail due to the effects of cosmic radiation. Cosmic radiation originates from our own sun as well as from distant stars, exploding supernovas and black holes within our own galaxy and other distant galaxies. We don't experience this strong radiation here on Earth because Earth's magnetic field and atmosphere provides very good shielding, so protection against cosmic radiation. However, for instance, Mars lacks a global magnetic field and has only about 1% as two reasons: costs and performance. Radiation-hardened chips are significantly more expensive compared to the consumer chips, and they are also lagging in performance. Commercial off-the-shelf chips are used for non-critical and short-duration space missions. For instance, in the famous first stage of the SpaceX Falcon 9 rocket, the chips do not really need to be radiation hardened because the first stage of the rocket does not go to the orbit, but only travels 80 kilometers skywards and then after separation returns back to the Earth. That is partially how SpaceX can drive the costs down with respect to the other spaceflight companies. Now I would like to discuss the approach of the SpaceX, because SpaceX is clearly ahead in the commercial space, and it's super interesting how they build their space onboard computers. As SpaceX is a private company, it is really hard to find exact information about the hardware they use because they do not reveal it. Anyway, I was able to find quite some information. As I've already mentioned, redundancy in space is a must. And in case of SpaceX, chips redundancy is built in from the very foundation. So there are 54 chips in SpaceX Dragon spacecraft. Those includes different types of processors and microcontrollers. Each Falcon 9 stage has stage-level flight computers to handle stage control functions. They've got 3 microcontrollers on each engine. So each Merlin engine is...
So what is a microcontroller? Input and output peripherals. Yo. Yeah, I gotta go see Alexi. Wait, you respond like, yo, why don't you answer that right now? Uh, yeah. It's okay. That's cute. Hmm. Yeah. It's okay. You can just start getting like a gift thing. I said you could just take his gift without giving him anything back. Yeah, what the hell do I even know? Yeah, but I don't know nothing about what it's like to be a pirate from Philly. Yeah. Yeah, I don't know. I don't know. Or it's just really, really cold, so I can allow it. It's just streaming too. That's okay. The glad Luca ended up calling or texting me. I said I'm glad Luca ended up texting back. Yeah. Well, it's good that you texted him though, right? Because he was gonna tell you something. He was asking for your opinion. Or was that did he already buy something? What? Mm-hmm. Nice. Yeah, no, it's okay. Are you gonna work on biocatalyst after? I was gonna do that after I came back from DC. I was working on some other stuff this morning. So no, we're about to go later today. Like Okay. Small single or a small computer on a single integrated circuit. Wait, so are microprocessors and CPUs the same? But there was a time when not all CPUs were microprocessors, as they were built out of boards full of chips instead of integrated onto one silicon die. So a microcontroller is a microprocessor was built. It's a microprocessor built in RAM, some features of ROM, flash, ROM these days, and I/O to make a small standalone system. It is generally intended to be embedded in an electronic device and run a single program, and they run in real time with low latency. They aren't intended to be general purpose computers that run arbitrary applications, want cheap low power, so have dedicated external address / data bus PCIs, though many could give up some I/O lines to be used as bus pins. Most have the high-speed signals as are integrated inside the chip, making it easier to design boards around them. Okay. Microprocessors are CPUs, but there was a time when not all CPUs were microprocessors, as they were built out of boards full of chips instead of integrated on one silicon die. Microprocessor was literally a CPU on an integrated circuit. It might have more RAM on board than most microcontrollers, but that is cache RAM. PC CPUs are fairly high-end microprocessors. Confused matters, it may have multiple chiplets these days, but one or more complete processor cores on a chiplet. You may have cache memory, many more processor cores, and some glue logic to join them together in separate dies. The cache memory is just to get around the limited speed of the external memory interface, a memory that would otherwise slow down the processor and store temporary copies of data, with most recently used data in main system memory. And a lot of other functionality like GPU cellular radios. So PC CPUs may have integrated GPU and some built-in, I/O devices. Laptop CPUs may integrate a lot of functionality on GPUs. Okay, so difference between microcontroller and microprocessor. CPU. Questions. What is the difference between microprocessor CPU? Okay, so someone's here. I guess an integrated circuit is a closed circuit, and seems like you can have multiple integrated circuits. So can a CPU have multiple integrated circuits? Both your definitions are incorrect. So what is the difference between a CPU and integrated circuit? So all CPUs are integrated circuits, but not all integrated circuits are CPUs. I think this is interesting, yeah. Can be a combination of multiple integrated circuits. This usually doesn't happen anymore, or single integrated circuits that can do calculations based on instructions in memory. So there are other types of integrated circuits do other things besides calculations. Like RAM. Okay. So that's interesting. I finally kind of got that definition down. So an integrated circuit can refer to a more broader field of different types of semiconductor chips, and CPUs are more focused specifically on the processing of instructions for some type of computer or electronic device. Integrated circuits, these guys can be a whole host of different types of electronic semiconductors. So some of these include CPUs, but you also have things like RAM, random access memory, some memory chips, also maybe even graphical processing units, GPUs. And I think in this case they had talked about mixed signal amplifiers, data converters, regulators, power supply controllers. Yeah. I don't know what a multiplexer is, but FPGA, field programmable gate array, I feel like it's probably another one. Okay, multiplexer. I guess it's kind of like a neural network almost. You have a bunch of inputs and then you have a single output. Or, yeah, I don't know. Maybe that's not the best thing. Okay, so that's interesting. Chips used to guide space rockets. Chips used for processing instructions for robots and sensory data. Quantum, maybe. Chips used for quantum. Quantum are able to model qubits. So I think these are quantum bits. Qubits. Right. So there's a few tailwinds that we can kind of see here in the semiconductor industry. There's a lot here, and it'll be interesting to see how this kind of plays out. Now I do want to I do want to take a look at Intel, because I feel like Intel is a company that is really undervalued right now. Or not undervalued, but their stock has been taking a beating, and I want to find out why. And see if there's any value in the future. TSMC also, Intel earnings. Intel SEC filings. Okay. So I guess Intel owns shares in these companies. Yeah, let me delete some of this stuff. There's a lot going on here. Okay. Let's do, yeah. Okay. Yeah, I don't really care about their revenues. So let's try to summarize Intel's strategy. So this is what Chris Miller said. Chris Miller thinks that Intel's strategy is to operate pioneered by Pat Gelsinger. Okay, so it seems like they reduce the technological gap in capabilities with TSMC and Samsung. So this also creates a new foundry business segment to produce chips for Intel and its competitors. This seems kind of suspect. Wonder if anyone actually would want Intel to manufacture their chips. TSMC has a non-compete agreement with its customers. It will only produce chips, never compete in designing chips. Intel does both. So this is kind of what I'll say right now for Intel strategy. And it's hard to say whether or not their new foundry business segment will actually do really well, but I think there's a few tailwinds here in the sense that the US is offering a lot of subsidies and grants to help Intel cover the cost of creating their new or upgrading their existing chip manufacturing facilities. So there could be some government intervention to make Intel's business model succeed. I don't really know how to calculate the probabilities for that, if that's even possible, but it could be interesting, an interesting idea, an interesting thought. Right, so let's do Intel business segments. So we have Intel products, Intel Foundry, all other. So some big ones here are the clients, computing group, data center and AI, network and edge. So Mobileye, I think, is there. Let's see, Altera, mobile, other. So this is interesting. Consists substantially of inter-segment product and services revenue for wafer fabrication related products and sold to Intel products. So it seems like the way they're actually recording revenue is they're booking their own production of Intel products as revenue for the Intel foundry. Which is an interesting way to do this. So Intel foundry. They seem to be booking the recording the production of their own chips as revenue for this business segment. Does this might produce misleading results? Misleading metrics if they include their own chips. Okay, yeah, so it seems like they are doing that. So Intel is spending around 4 billion on its own production for its products, and about 15 million is, yeah, it seems like 15 million is actually being used on producing other chips. Okay, so it seems like, right, the foundry business is really taking up a lot of this, really bringing down the profitability of Intel itself. Okay. States of Intel today. It's May 25th. Let's do May 2024. So, unprofitable due to heavy capex and R&D spending for on its foundry business. I think without it though, total Intel products revenue or without it, the company would be profitable, it seems like. Okay. Has owner non-controlling interest in Arizona fab Mobileye IMS Nano Fabrication. So what is Arizona fab? Interesting. So it seems like, yeah, Intel is using co-investments to help finance some of its foundry expansion. It's interesting to see this. Yeah, maybe it's not good to use Reddit as a source of truth, but哎，
你这有空瓶子吗？
就俩，
就俩。
也有，正好现在没有空的时候可能不够。
那个空瓶子我没搁那儿ice。
You wanna go in like 30 minutes?
再等会儿，外边90度。我刚回来。
那你去哪了？
一般那个挡住一点，那太阳晒得更热。
That's nice. I'm just kind of hungry. Yeah.
那行啊，稍微能打一个号。
Okay, okay. Discussion on Intel. Plus Brookfield co-investment. Yeah, okay. So what is IMS nanofabrication? Electron beam lithography. So I guess this has to do with the actual production of chips. That's why they sold some of it too. Combined 32% minority stake. Okay. So it's nice to see a increase in revenue. $47,000 in debt. Yeah, it's a lot. Short-term debts. You know, I have to say the interest expense is not bad. Let's see. Debt. Okay, I don't think they really have specifics here, but yeah, maybe take a look at their most recent annual report. $54 billion. Okay, so yeah, this is maybe more in-depth overview into kind of their strategy. Let's take a look here. Okay, so they're throwing these 5 buzzwords here. Intel believes in the 10K report. Intel highlights 5 key tech superpowers. That will drive an technology industry in the future. So ubiquitous compute. So I think, okay, this is actually a good thing. The idea that everything in the world uses computer technology. Microprocessors / micro pervasive connectivity. The idea that everything and everyone is connected. So this is the Internet of Things. Cloud to edge infrastructure. So unlimited scale capacity combined with unlimited reach for lower latency and higher bandwidth. So these guys are still going with x86 and XPU. Okay, so cloud to edge infrastructure. I'm not entirely sure what they mean by this, I'm not gonna lie. So they're saying here unlimited scale and capacity combined with unlimited reach while simultaneously addressing the need for lower latency and okay, so I kind of understand what cloud means, but what does edge computing? Closer to sources of data? Not. What does that mean? The cloud versus the fog versus the edge. Whoa. I know. So I think cloud computing just means to move your applications and data to big data centers managed by skilled companies. So Amazon, Azure, Google, and an a la carte. So buy what you eat style. Business model. Edge computing, just means to add this move the application and data closer to the source. Example, storage could be is a self-driving car that needs to process the immense amount of sensory data around it in order to make sure it doesn't crash. So Intel believes it needs to capitalize on these two trends by providing semiconductors that's process and store data. Okay, I think that's the basic idea here. Intel wants to be able to capitalize on the increasing shift from cloud computing, I guess from on-prem to cloud computing, and then edge computing. So this is processing done and storage of data very close to the source. AI. Basically competes with NVIDIA here, and then sensing. Empower electronic devices to act like perceive sensory data. Okay, so Intel has Intel products. Intel, so focus on X 86 and XPU instruction set architectures. 86 red. So is X is set and assembly language the same? Company that created a processor defines the instruction set, the machine code or opcodes, whatever term they or you use for bits and bytes, the processor decodes and executes. Very often the company will produce a document assembly for those. Okay, so our instruction sets and assembly language the same, and we could call it a Stack Overflow. Instruction set is a set, like in math, of unique instructions to a microprocessor. Okay, so what is a processor versus microprocessor? Quora. Assembly language is a way to construct instructions for the processor to complete, and the assembly language itself can change depending on the instruction set. So is x86 a instruction set? Is a instruction set architecture? All an IC really means is understanding of what numbers. Defines what numbers, bit strings have what meaning to the processor. This is interesting. Oops. Okay, I think I'm gonna save this for now. I'm getting kind of hungry. I'm gonna come back in a sec. So what is the difference between x86 and ARM? So how does the ARM architecture differ from x86? Oops. Yeah, okay, so it seems like there are some technical details here. But Intel is going to be focusing on their x86 and then XPU instruction set architectures, it seems like. But from what I'm seeing, just based on some news articles, it seems like a lot of people, Apple, Qualcomm, Microsoft even, are moving away from the x86 into ARM type chips, and also the RISC-V chips or instruction set architectures. So I think CIC. So the x86 has the uses the complex instruction set computer. the CISC architecture. ARM uses the RISC. So I feel like reduced, probably. That is considered more efficient than x86 CIC. So why is ARM more power efficient than x86? You were so wrong. Okay, so I'm gonna read this because there's also some technical components here. Difference makes ARM energy efficient. Okay. This is Reddit. I think this is, okay, Stack Overflow. Okay. Yeah, I'll be back in a sec. Okay, so probably gonna spend another 20 or so minutes here. But I think, all right, let's go back to the 10K then. So we have a very high level overview here of the Intel products, specifically what an instruction set is, how that is different from assembly language, and then also what a instruction set architecture is. So at our core is the x86 computing system, which supports an extensive and deep universe. So there's also it's an XPU. So GPUs, Intel's response to growing need for where's our accelerators? For specialized chips, complex tasks, GPUs, FPGAs, or IPUs. IPUs. Infrastructure processing unit. Okay, so this is Okay, this is kind of funny. Intel IPU. Okay. So I think these FPGAs are like really small microcontrollers. Field program. So this is getting sidetracked by FGA and high frequency trading. state machine. Oh man, I totally forgot about that in my 330 class. Block diagram for an asynchronous FIFO. Programmable PGA Stack Overflow. Similar concept to microcontroller, collection of CPU and input / IO memory, but the FPGAs It's $1,000, damn. Okay. Alright, so I gotta go now, but Intel's products, they're focusing on x86 and XPUs. Okay. Okay, so this is going to be really, really interesting here. Okay, yeah. So I'm gonna it'll be interesting to read their MDNA too. But yeah, I'm gonna probably stop the stream here, and we'll catch you guys in the next one. So thanks for tuning in. Peace.